Hello, everyone. Thank you for joining us today for Where Did Your Ore Go? So we will just do a few housekeeping items here before we get started. Um, if you are having any audio issues, which you might be not able to hear, I'll put a document in there. I would encourage you to call in. You can also then use headphones as well. Sometimes that helps. If you have any questions during the presentation, please put them into the Q&A part. Do not put them into the chat. Please put them into the question and answer area. We will do any questions and answers at the end of the recording of the webinar today. And if we run out of time today to go through your different questions and answer them, we will reach out to you individually and answer those. We will also have some polling questions for today as well, so that's something to keep an eye on. And then other than that, I believe the recording will be scheduled and that will be sent out to you after the conclusion of the webinar. On that note, I'm going to go ahead and turn it over to Ravi, who will go ahead and get us started. Ravi, if you're able to share your screen, we'll make sure that's coming up well too.
Fantastic. Thank you, James. Can you hear me okay? James, can you hear me okay?
Yes, I can.
Okay. There's some
I can see your screen.
Awesome. Yeah, so hi, everyone. Good morning, good evening, and good afternoon, wherever you are joining in from. I'm excited to kick this off. This is an interesting topic, close to my heart. Really talking about the dilution factor.
Ravi, it's not showing full on your screen. It's showing in PowerPoint mode.
Got it. Okay. Good point. Let me get started here. Let's give it a minute. There is a bit of a lag at my end. I'll see why it is that way. Let me reshare. As soon as I turn into a full screen, it's just my screen is frozen. There is never a webinar without any technical difficulties. I may have to just run it without full screen mode. The reason, as soon as I turn into full screen, it just completely froze. I was not able to move any slides. So we'll try this again. 1 second.
Yeah, the slides were showing, so if we need to do that, I think that would be fine.
Yeah, it was strange. Hopefully, I think it will still be able to show the content, and we can move this along. Share screen. Make this a little bigger so that you all can see, okay? All right, let's try this again. Well, good morning again. The topic for today is where did your ore go? And we're going to focus a lot more on the dilution reduction. How do we plan selective digging with confidence? These are the ways you can deliver the actual kind of ore polygons with a data-driven method. That's the whole idea about this session today. So I want to start with a story. A few years ago, I visited a site. I was standing on the bench and with a senior geologist and someone who has been in the industry for almost 20 years. And we were looking at the muckpile that has just been blasted. And the geologist pointed out on the spot and said, Ravi, I know my ore body here. I know exactly where the ore is in the ground when I model the resource, which means through my block model. But once we hit the timing and initiation here, I'm just guessing. And he wasn't guessing, literally, because it was more what happened after the blast when you fire the shot. That was the guessing part. He was guessing because blasting is chaotic. It is essentially has many variables, and it's the only part of the mining process where we accept a black box regarding material movement, right? We have so much engineering equations, so much uh, data point about how to design, how to time. Essentially, this material movement is always becomes a black box. So today we are going to talk about opening this black box, right? So we are not going to talk about so much about kind of how to do digital things or other buzzwords. We are going to talk about physics, essentially, and then how the data-driven approaches, which means building kind of more advanced model, which will stop throwing money kind of into waste stuff. The reality of the problem is we all know this issue. You drill, you sample the assays, you build a beautiful resource model, and you have sharp polygons in the software, which defines the ore and the waste polygons, then you blast. But then these polygons just not match what the actual outcome is, right? So that's where the majority of the issues comes in, and we will talk about what are the approaches we all can take here. And if you're relying on just on visual estimates, going out there and measuring and doing again sampling by manual methods, still it's a good data, but it's not a full proofing your material movement. And what I see is just kind of, if you're relying on just 2D based estimates, you are dealing with what we call phantom shift, right? You measure like 2 points, and then there are actually other areas where polygons are shifted. And then what happens is you send a high grade ore to the waste dump, and you send waste to the mill, which is kind of where your dilution continues to increase then. And some studies have shown that failing to model this properly causes ore loss of roughly around 30% and dilution of over 50%. So why we have been doing with the same approaches? Because the traditional approaches are still very strong and good, but it can improve from incorporating and augmenting the both pre and post blast models then. And in generally, it can help alleviate that phantom shift that comes in. So agenda for today is we're going to look at the dilution problem, the current approaches and its limitations, then the hybrid solutions, what AI plus physics model can augment that newer ways of looking at this problem, how it works, which means traditional kind of approaches versus the newer approaches, what type of data input and output comes with it, and building a post-blast block model from that, and then how the feedback loop helps you in this iterative design and material movement process. So as we can see, this is a typical problem you identify in the beginning, that you have a waste and the ore problem, and you want to kind of make sure that your polygons are very exact. The ore zones comes in form of mixes. And you want to separate that before you have a really good understanding of how you build a block model. And then based on that block model, you're assigning each blocks a specific characteristics of the ore. Either it could be low, high, medium grade ore zone, and you want to maximize the throw based on your blasting methods and blasting process that you have created in your mind. And that gives you the boost into the mill performance then, right? So this is kind of, the crux of this entire problem is. Before I go into the further discussion here, I want to throw in a quick poll about how are you currently measuring the uh, or polygons, or just your measuring of the material movement. So let's start that. Quick poll will pop into your screen if you can participate. So the question is, when you currently mark out your dig lines after a blast, what is your primary source of truth? We'll give a few seconds. Okay, so still some votings are coming in, so we'll give another few seconds here. Okay, so we'll publish the results. So it's great to see that a lot of the methods of the measurement right now is physics-based modeling, physics simulation, which takes all the parameters, and that's kind of, the material movement, can be modeled here. And then the next majority of them is essentially we stick to the pre-blast kind of polygons as one of the methods there, which, usual suspect, it's physics-based simulation. Obviously, DM solvers are the most reliable method at the moment. So continuing back on the presentation here, so we understand what is the limitations of the physics method. Essentially, you have a traditional exact same model that you can run for each different scenarios. And then you have a great control plan built in. What does happens is with this traditional physics-based simulation methods, we're going to go into more detail how each kind of discrete element model and methods are reliable, and some cases where the constraints are high enough where the performance goes down, right? And how you can augment that with new type of data and new type of information that you're already creating from your each blast. But the typical ones is essentially your ore zone classification methods may not have like a good exact geological boundaries at the each blast hole level. That's where we see a lot of classification problems on the muckpile boundaries, which means you have an assay hole and you have a blast hole, and your assay holes, you're not sampling for each blast production holes there. So that's one of the main issues that we continue to see with the traditional DEM methods here. Now, if you just think about the dilution problem in general, blast-induced rock movement have like a lot of challenges in the grade control. You can essentially consider blasting is one of the method how we fragment the rocks, but the rock mass we rarely update for each blast. As soon as the blast is done, we are relying on the same geological model or same rock mass conditions that we have gathered in maybe our core sampling surveys or just regular surveys every month that has been happening, but it doesn't get done often enough for each blast. And that's where the fundamental shift kind of happens, which means your rock mass properties are changed after each blast there. Now, post-blast ore and waste boundaries, that is one of the areas where the rock mass can have a significant impact. So if you can update your rock mass information, that is going to give you a much more better understanding of how the material movement happens. And this displacement means this kind of original grade control model that you have becomes inaccurate if you're relying on the grade control model that is about 6 months old, or maybe just kind of few months old. So what if you continue to update that? That will help you in kind of guiding this over polygons creation there. That's what we will look into further here. So an unaccounted displacement, that's where it leads to the ore losses and dilution problems occurs, and just continually ignoring the dilution problem cascades more problems, down the line into your, mill performance, as we will see more in future slides here. But failure to account for the blast-induced movement is considered as one of the main factor for every ore loss situations, where valuable ore is sent, to the waste dump. Likewise, if a waste rock mixes into ore, it increases the processing cost, and it obviously lowers the, it depletes the deposit, really fast. And that's where we have seen like economic performance suffers, your bottom line goes down, and the post-blast movement is not modeled well. So what are the scenarios, that you can model well, right? That's where we will see more here. But just continuing, why going more better into the problem itself, right? So blast movement is highly variable and non-deterministic kind of, situations here, which means it's not like you give one equation or you give like 5 inputs and it will exactly produce the same output here. It is very variable, problems here. So because blast induced rock movement is inherently a 3-dimensional phenomenon with extreme variability and no deterministic kind of pattern. You have your rock mass properties, you have the design, you have the energy properties, from the explosives parameter side, and then overall in general, the environmental conditions as well. So within a single blast, your horizontal displacement can be as much as like 50% from the average based on what you have actually designed. So interplay of factors such as design, rock properties, geological boundaries, that also influences the material movement, which makes it very hard to predict it very accurately. Physics model performs well, but that's where the constraints will start to create then. And the rule of thumb, as I kind of, we have seen, is if you can measure it with your method of, 2D method or using the other measurement techniques where you have a blast movement monitorings, which are essentially the sensors as well, which has been the gold standard for quite some time. And you drop a sensor in the hole and you blast and you find that sensor. It works. But here is the catch. You might have 5 or 10 sensors in a massive block. You get a vector that says the spot moved 10 meters, but then the rock movement is usually non-deterministic. And I was reading a study recently that showed horizontal movement again, which is mentioned here, is about like 50%. And if your sensor moved 10 meters, 20 meters away might have moved 15 meters. So you can see very reliable way of measuring the material movement, but because the sensors are moving every 10 meters or 20 meters, you still have that displacement gap that cannot be avoided, right? So you may have very confident measurement, but it's limited. So then the other approaches, as we kind of will continue to discuss about the physics approaches here, but that's where we see it's very variable and non-deterministic problems here. So the other approaches, as I mentioned, I already talked about the blast movement monitors, the physics-based DEM simulations. And this essentially, it's the gold standard right now. for every type of movement and the modeling. It can very reliably predict how the material movement can, and it takes all the parameters, rock properties, explosives, energy, but it is still not accounting for the historical data that has been generated from the post blast. So the learning part is missing. And as I mentioned, if you can update your grade control model instantly after each blast, that is a valuable piece of information for you to consider after every blast. Where the ore polygon, I talked about the phantom shift. If you can incorporate those phantom shifts for each blast, post blast, and then combine with this model, you will start to see the mode improvement. The discrete element modelings, they are, in my opinion, they are amazing. They simulate every single particle colliding. The problem, they are very slow, right? So, and you can throw in a lot of heavy computing resources as well, but it's still, the way it works is it's a set of tasks that works in a step-by-step fashion. You cannot parallelize it. So you're still relying on very long hours of kind of running this simulation, and sometimes what happens by the time the simulation is done, your blasting and your digging is moving faster. You've already dug out half of the bench, and it's also incredibly sensitive to inputs, which means someone needs to know how to operate these models into a great detail before you actually kind of master this physics-based models there. For an example, I've made a lot of mistakes. If I just change the friction angle to a certain degree of sensitiveness or my explosives energy, my entire prediction and the model fails. So that's where it really highly sensitive to the input. The other empirical approaches, kind of, as we have seen, is get 5 meters, like, heave measurements that you have. This is fast, but it ignores the geology. It ignores the specific timing of the blast. And then it's basically a coin toss, right? So that's another method that a lot of these sites that I have seen. So we realized kind of, we needed something in the middle, which means it incorporates the physics-based EM simulations and the AI models here. And I also want to touch about just only independent machine learning models as well, not considering the physics-based simulations here. This also is not reliable, and essentially it can learn from the data, but it's still a very non-linear pattern from the historical blast that has been created. It can predict displacement accurately, but they miss the inherent physics of how rock moves. They don't model each rock-to-rock kind of particle interactions, the gravity and swell in the muckpile. That is the key important part. So just by itself, independently, machine learning is also not that reliable, as we have seen. So how do we answer this question then? Can AI and physics predict 3D movement reliably? So the approach is here, can we at least build a model which can be combined together with the physics DEM-based model? And then there is an AI component where it will learn from the historical models how the rock moved and the ore polygons generated, and we feed that into the AI, the actual physics model, to build this material movement prediction there. So the way to do that is it has to combine an entire site learning, which means every time a blast is happening, we feed that into the model. And so the individual constraints that comes in, it can be addressed with new type of data. Then also the behavior of each blast that has happened with changing rock mass, changing kind of, the updation of the new grade control engineering. That is more the physics side. That data is highly useful into that integrated model. So our goal was kind of simple. You provide a high resolution data sets with the uh, drone models, as well as the incorporation of all the design elements, and then the actual physics model, which creates the new type of data, incorporate it, and then run it through the AI models here, which helps in aiding the designs. You can iterate it, and then also build the new post-blast muckpile models more reliably then. So, so we're going to look at what that hybrid approach is. Now, I may go into a little bit more technical here, but I think it is important to explain what this data type looks like. How do you run the model? We're not going to actually go into too much detail about what is the neural network here, but at least it will take you to the understanding of what this kind of, as I mentioned, the black box, right? You know, what's the input parameters and what's the output parameter looks like. So hybrid framework, it incorporates the AI model that has been trained on the site calibrated data. So your drill holes, your geology data, your rock mass data, and then the actual survey data. Now you have the discrete element physics model data, which is kind of the additional input, which then simulates the blast predictions, as well as the ore distribution models there. So the input can be your survey files, either geotiff, orthomap, digital surface models. Then if you have the timing patterns, those can be incorporated from as a CSV, or if you can design it in the existing softwares. Then also the model generates the output parameters, then it feeds back, then the DM solver runs and it generates its own parameters. It then holds the particle locations where that XYZ vector movement has moved, and it holds it and creates its own new record. It post-processes it and then runs the AI model again. So this method is called the deep learning method, where it interprets site-specific design parameters, and then it serves as an input to the particle physics-based simulations here. So it becomes a lot more informed, and what as a result you get is the post-blast 3D block model, and with an ore polygons that comes out from that. A little bit going more into the neural network itself, which means you have a repository of the data, which can be the geospatial data, digital surface model, blast design, geological and geotechnical data, and then the block model. It gets fed into this three-layer neural network, and a prior physics knowledge is captured, which means you have a DM solver that has already been run. So it has already recorded each XYZ vector movements, and it has created a database of last, let's say 10 blasts that has occurred, and it has a database of each movement XYZ with different rock mass conditions. So it is already sorted out, and each particles is being labeled according to the rock mass properties. That's where this new type of fundamental understanding comes in, which means we have a data set, and then we have a DM solver. We created a new type of data from it. So as you can see, blue particles, which is a trained particle, and then red particles, which is unlabeled, which means it's predicted by the AI. So DM solver predicted, we know exactly what it was, we labeled them, and then we fed the new AI data that has been created from the AI model itself. We feed it again into this learning process. And that's what predicted the next state of the movement. And consider this process can be run again and again, and much more faster. So what you're capturing is every 5-meter block, the movement every time for all your historical data, that you can understand what has happened for each blast. So that's why it is important that prior kind of physics simulations that have been run, and you use that data to iterate the AI models then. So unknown components, as you can see, are represented by neural network in the red, which means AI model did not know, which was one of the limitations of traditional machine learning method, that it did not know the actual rock movement. Now that rock movement information is coming from the DM solver. Combining this, we predict and iterate the next set of process. Going into the input parameters here, so you can also input site-specific factors such as rock properties, density, UCS, and of course the blast design details, including the loading, charging, as well as all the design parameters here. So source data, as we see, what the source data means is you have the AI simulation solver, which is a combination of DMs, which is a physics-based simulation. So we look at the digital elevation model, that is one specific input that is most needed. And why? Because each digital elevation model, AI uses pixel by pixel positioning to incorporate the hole position as well as the timing pattern, so which we call geospatial based timing, to incorporate for the AI solver. Drill hole distribution, which is array of 3D endpoints. So you have X, Y, Z, and that's been incorporated there. Timing, along with each kind of timing steps there. Loading, which has the actual energy distribution, ground material properties, and the explosion properties as well, and the block model. And block model is where your grade control models that has been built for each blast, as you're updating. Now this becomes a much more source of truth, how your material displacement will occur based on your desired conditions. I'm going to take a pause here and we'll launch into another poll. So let's go back. All right, so back to this, we'll start another poll. So this poll is, if you had to guess which invisible thief, which is essentially your dilution, is costing your operation the most money right now during the blast. So either it's ore loss, dilution, misclassification, muckpile shape, what would that be? We'll give a few more seconds since we still have votes coming in. Okay, so it's definitely the ore loss is where we are seeing the majority of the problems, including the dilution. So it's neck to neck there. Well, we'll resume the presentation here, and we'll address kind of why those two problems, ore loss and the dilution, goes hand in hand. So we talked about kind of what are the other limitations of the traditional physics-based model, right? So it's more the speed as well, how fast you can run. Sometimes creates advantage because if you can run more, if you can run again and iterate, what you will see is you will see a greater adoption of the tooling among the entire process side, which means the drilling and blasting people can run it. The department side, the geologists and the ore controller itself is not a part of only one specific segment when and where it needs to run. So digging a little bit more deeper into what was the accuracy that comes out of this model. So the neural network predicts key blast parameters, which is needed by the physics engine. And then it outputs this equilibrium pressure, movement velocity, the burden movement, and the crush zone radius for each blast scenarios. These are the outputs that comes out. And what we have measured as the actual ground truth blast that we have seen, at least the burden velocity that we have seen has a standard, mean square. We have achieved up to 94%, which means 92% of the predictions were within that kind of, range of the true value, the ground truth values that was predicted. Also, the model kind of provides the blast parameters. So for an example, if you're not satisfied with your blast parameters and you want to change it and see what predictions comes out, you can iterate that in the solver really fast. What if I change my delaying window a little bit, more? What if I can change my energy distribution a bit more? What that kind of, change looks like? And that's where the deep learning acceleration cuts parameter and estimation times from hours to minutes. Because you can parallelize this physics modeling more accurately. And there is a specific term for this. It's called physics-informed neural network, which means you can really parallelize the equation to run in parallel. So DM physics simulates rock fragmentation and then also the heave displacement. The displacement, the discrete element model, as we are seeing the rock bench as well as the collection of the spherical models, as you can see here, which is each own vector movement. And it's defined by kind of the discontinuity, any type of large movement, small fragments that gets broken, including the rock mass parameters. And essentially how the taken from the traditional physics modeling as well, which is more Coulomb criterion, which means how the bond breaks, which means essentially how the fragment kind of breaks here. And this gives you kind of the each movement at any specific point of time, and it models gravity, explosive forces, collisions, and frictions during the blast here. So that's the traditional model. So you don't need to go into too much details what I am seeing, what I'm explaining here. But in terms of the solver itself, all you need to do is just input the parameters, right? But it is important to kind of explain, like, what goes behind kind of the scenes here. But in general, if I have to explain how it works, so you have the AI, which means we train a neural network on thousands of data sets. You get a blast and synthetic simulations from that. It looks at your drill data, geological data, your timing, and then also loading. It doesn't try to simulate the particles yet. It predicts the energy profile. It predicts the velocity, and it predicts the starting conditions. Then you have the physics model gets run. And what it does, it is where we feed these AI predictions that just happen in the first step. It takes into that solver, the physics solver, because now the AI is already done the heavy lifting of all these predictions, which means burden velocity as well as the energy profile predictions. It feeds that into the physics engine. Now you can run it really fast because it has this data output has come from the many historical learnings. Now what you get is the result after this, which could have taken several hours. Now it's in under 10 or 20 minutes. Now this is where you generate the vectors. And in the muckpile modeling, the vectors are the key. But not just that, the vectors in more close 3D dimensional, and if you can get it within 5-meter blocks, this is where you get a lot of more good information about the precision digging then. And that's what you get now on new vectors within each 5-meter blocks. that you can generate and export the 3D blast movement over polygons then. So this is what exactly showcasing in these pictures, which means you have the drill patterns and then the new heave model that comes out. And this is a simulated the digital model here, which means this picture that is being highlighted, it's not an actual blast. This is being generated as a digital twin model from the AI predictions here. Looking at how it helps in your dilution and the ore losses, which is one of the whole questions here. So each particle in this simulation carries a tag, or what we call it's kind of tracing it back to the original block model, right? And in your original block model, you have assigned your XYZ, you have assigned the ore properties there. And now, after as it moves, it uses that tag to allocate the movement vectors. And now you can use these movement vectors, and the model automatically assigns those movement vectors to each resource in a polygon stand. And as the material displaces, you can easily then track where the waste is going, where the ore is there, and what is leading to kind of more dilution scenarios here. And if you are seeing a greater dilution, you go back and run the simulation again with different iterative parameters then, until you get kind of the desired results that, our goal is to reduce the dilution by 3%, 2%. Here is what the parameters is giving us the better results. So after the blast, what happens is the final positions of all the particles comes out. And that's what you are looking at, the full ore and the waste distribution throughout the muckpile. And you can also start to predict where there's potential scenarios of the mixing, can happen. So post processing, what you see after the blast is generated. So for an example, if this is considering is your blast, once you see the mixing scenarios, how it's happening, which timing parameters is not a desired parameter, you can start to iterate those more proactively then. So you get a post-blast block model, which has updated ore in the waste zones, directly controlling your excavation planning. Now, after the additional inputs are being fed to the AI model, it also stores that original pre-blast model that can be overlaid onto the post-blast model. So the detailed data it can be exported to the mine planning softwares as well, which is where you can update your grade control really fast. You build your new block model that is coming out of this instantly. Give it to your dispatch system, to fleet management systems more instantly for better analysis here. So let's look at the more kind of full-scale bench setup, sort of like a case study. This is a simulation we ran for one of the large mine, and you can see kind of the swell a little bit here, but just in general, you can see from the shift perspective, there is a uniform shift here. The material near kind of the free phase here, there's a bit of a swell. Material near the free phase moves a little bit further. And if this can be iterated more properly with this both AI and the physics-based simulation, you can control this kind of this swelling, or at least have a better understanding of the swell factor, and that's where a lot of the ore waste mixing kind of happens. Then, so what I want to highlight is this ability to factor in and simulate a lot more faster gives a lot more advantage here. So this drill hole data set has a lot of 3D coordinates of each hole. It was simulated, and then blast pattern in this example was loaded, and the AI calibrated rock properties. So this one, the predictive kind of calibration properties were generated from the AI and which was fed to the physics model. Now, case in point for this example, the dilution factor that was generated, which was later utilized for the next blast as well to control the new parameters. So it became as an input to the next blast. Although this blast resulted into a heave, which was more not ideal, but it was used for the next blast to again control the improvement then. So post-blast resource generation model here, and we're going to look at how the muckpile formation and redistribution pattern occurs. So the solver continues to check where the movement is happening, and you can simulate this in real time, which means when I say real time, as the model generates these outputs, you can run and pause and see where there's information that you're looking, where the dilution is occurring more. You can kind of see that in the more interactive fashion. So if the material near free phase and the surface experience greater lateral displacement, why is it happening? What was the cause of that? So now you go back and change the parameters. Is that lateral displacement still occurring? So those you can iterate in a much more simulated view. It can also generate cross-sectional views of the post-blast, so we can have a very distinct ore zones and the waste pockets that's coming out from this. You can simulate here. Also, the timing is always one of the key things that every blaster aims for to get it right. What if you simulate the timing scenarios more proactively from the dilution factor scenarios here? So that's I see the redistribution pattern that usually comes out. It gets a lot more closer to what you're going to execute there. So we'll look into the selective digging, how the output helps in the selective digging here. So before we go in there, I have the last hole here. We'll kick that off. So the question is, what is the biggest barrier is stopping you from running advanced blast simulations for every single shot? So the time, complexity, data quality. You have tried models before, but it did not work. You give it a few seconds. We'll give a last 5 seconds here. Okay, so definitely what's taking the first spot is the data quality here. So we'll look at the data quality, the input data, as we see often in the physics models. The data quality is always the biggest factor. If you don't have a right input, it can really be very sensitive to control the physics model outputs. And that's where I truly kind of believe that, once you incorporate a learning from continuous data that has been collected, that becomes a lot more guiding factor for this advanced models now, which is incorporation of AI plus physics model. We'll return back here. So how it informs your selective digging. So always boundary evolution that occurs, it's one of the key things that guides more the production planning, which means as a mine manager, how do I use my machines more effectively so that they are excavating properly, and then what comes to my mill gets processed properly. And that's why the ore waste boundaries are such a critical factor of everything that gets done from the blasting perspective. So ore waste boundaries that has usually a displacement of roughly 2 to 8 meters from their original locations uh, can create kind of critical update problems on the grade control. And so as you can see here in this pictures, the first picture is mostly you have a blast bench face. It corresponds to essentially just the natural colors, but once you have the block models, it will assign the colors factors, and once you blast it, it will map each block to a specific resources here. And that creates the another type of ore polygons. Each five you can define if you want every 5 meters or even lesser, and this exact polygons can be fed with XYZ information to the fleet management systems into their dispatch units here. And this can be the guiding factor for the next blast, which means what we generated and what we are going to process. It's in sync now. And the updated ore map significantly has a way to control your dilution factors here. So what it allows you to do is grade by grade visualization exposes where the ore boundaries are, as you can see. And here, this does not have the actual block model data, but pre-blast polygons, usually does not limits the dig limits before, but now after the blast happens, you can overlay the pre-blast data, and then the new post-blast data that has been generated with the resource polygons becomes the guiding factor for those dig limit then. And you can calibrate the next blast accordingly from the dig limits that has been created now. So accelerated computing, as we talked about, the hybrid AI-DM approach gains significant computational efficiency among the traditional full physics simulation. Usually linear scaling is always a problem in the physics models, but parallelized distribution with the new approach gives you a much more better execution time, and then also a new type of data. And then in the future, what we are also considering is with the GPU acceleration, you can enable millions of particles near real time without kind of sacrificing the accuracy there. But the big thing that I also see, if you are able to continue to do a lot more with your grade control practices for every blast, right, you can push this data instantly, as you see, to your mine planning systems. So the framework is, you have your updated block model surfaces that gets pushed as soon as it's generated to your mine plan softwares or grade control packages. Now, these automated workflows has an advantage, which means every time a new dig limit is kind of created, new grade control, it guides the other teams, such as blasting team or the other survey teams, that they should just refer to the new updated model to design the next phase of the blast with that proactive improvement that is needed. Including, we are seeing the biggest advantage also is if you are able to generate these ore polygons a lot more faster. You can feed, if you're running an autonomous equipment, it just instantly dispatches to the machine control softwares, and these machine control systems, will guide the digging precision based on these ore boundaries then. So the current limitations, what I see in this approach, the accuracy of these predictions depends on the quality of input data as well. So if, or just like as I mentioned, the physics model is sensitive to the data input, the AI models is also sensitive to the data input, which means if garbage in, garbage out, like, if there is a lot of data which is not that reliable, the AI model will also not perform well. Such as errors in geological block model or imprecise drill hole locations can really kind of, mess up the simulation results here. High quality survey and geological data, right? So that's if the survey is not good with the good resolution that has an impact on the AI model as well. The DM uses the spherical particles approach, which sometimes can be very blocky shape, and that is current limitations because it uses the rolling resistant method. Our future work will be to actually use more angular method that kind of mimics the fractured nature of the rock itself. So also the goal will be to develop self-calibrating system. At this moment, it needs a lot of supervision from the AI engineers who are actually doing these calibrations. So every time see a new data that's been calibrated to make sure that the new prediction comes out, it is more accurate. But the future would be to design a system which is more self-calibrating. Where I see also this being evolved is in the incorporation of the hyperspectral information, which can map the chemistry of the rock content. So if you have a post-blast, if you have done the pre-blast hyperspectral scan of the phase, you know what's the chemistry and the ore content is. After the blast happens, you fly with a drone again with hyperspectral camera sensors, which can map the chemistry content again. You overlay that information and now see where these kind of differences are. We rinse and repeat more, and it defines the rock kind of properties then. And so it gives more additional information what we are already doing, and that's where the grade control continues to evolve here. The big outcome from this is this approach is the feedback loop that I want to highlight. Is it's essentially, imagine kind of the shovel has a sensor. As it digs, it sees a material. It feeds that data back to the model. The model says, hey, I predicted the contact was at 10 meters, right? The ore polygon, but you hit at 12 meters. What if it updates itself for the next blast, right? This is the self-learning I'm mentioning, that how it can change the precision digging methods as we move into that area of real time here. So with that said, I would like to conclude today's session as we're getting into the end of the hour. It's essentially, this allows you to really gives you a framework to think beyond the physics model. And I want to reiterate that the physics models are the fundamental thing that is very reliable. We are just adding a new approach here. How do you aid a new type of information to have a consistent and more calibrated learning, right? So the days of guessing is over, where your ore went, right? And we don't have to choose between like one type of sensor data or one type of physics simulation, but we can combine them so that we get a tool which is fast enough and then accurate enough to save millions in lost ore. Thank you very much.
Excellent, Ravi. Well, we certainly do have some questions in our Q&A, so we'll go through a few of those. If any of our attendees have different questions they'd like answered, please make sure you put them into the Q&A part, not the chat. And then if for some reason we do run out of time or don't have a chance to get to your question, we will reach out to you individually, or if we need to do a deeper dive. So Ravi, first off, our question is, how do you prepare the data set for your AI model, and how are the inputs and outputs generated?
Yeah, so my advice is kind of really simple here. You start with what you have, which means start with your drone survey data. You have to have a high resolution digital elevation models. Then you have organize your drill design data or your blast parameters. Those are the kind of key inputs. Then you have the geological model data and any type of geotechnical information you can bring in. If, for example, if you have a historical backbreak kind of data that you can bring in. So those are also useful there. And after, from the learning perspective, the calibration, what you can continue to kind of evolve this data set to feed it into the model. The other area that I would consider more your block models. So if your block models are continuously being updated, that also helps in the calibration part of the model then.
Perfect. Our next question is, do you use post-blast drone survey as an input? And I believe this might have been around some of the ORBYM area in the presentation.
Yes, yes, that is one of the key parameters for the AI for the calibration. Utilization of the post-blast drone survey, and we take as much as kind of data that's been generated from the pre-blast, which each vector movement, and then we use that information, compare with the post-blast, what was the significant differences are there in the polygons, and then that gets fed back into the AI model.
Our next question is, what software did you use for the DEM modeling?
So DEM modeling, it's mostly we don't use the actual software itself. The physics modeling, there are tools. So there are NSYS, particle NSYS models are there. That's on the DEM modeling side.
Is there a pre and post blast rock mass balance? Is the pre and post blast rock mass balanced?
Yes, so pre and that's kind of a really good question. It doesn't happen often, right? Which means you may have a pre-blast kind of rock mass survey that has been done, or if you have already existing data, but after the blast occurs, it usually changes. So how do you actually utilize that information? That is based on the calibration, and that really depends upon the team on site, the geologist, and then also the team from the grade control side, if they have that data, and if they input that data of the updated new rock mass, that will be balanced then. But that information becomes sometimes limiting factor if nobody is collecting that just after the blast.
Next one. Since data quality matters, have you quantitatively checked how well both the synthetic data and your model uses the synthetic data it produces to match real blast data? And then there's a second part of the question, but I'll let you answer that.
Yeah. So we have done one comparison with the ground truth, and that's what kind of I had one slide which was predicting, kind of showing that accuracy there with the ground truth comparison, and we are open to kind of feedback here. And as I mentioned, this is something, it's a new type of approach, so it will take time to iterate. It will take time, and as with the approaches of as its new data is coming, the calibration and the continuous learning will become kind of more important. But what I anticipate is at this moment, the synthetic data that's been generated, it is reliably predicting that the burden velocity movement as well as the energy distribution. What we are seeing, that is where a lot of the reliable metrics are there. Now, after we combine with the physics model, our goal is to make the material movement more accurate, right? So, and that will require continuous, more iterations there.
And you might have touched on this a little bit in your answer, but I'll make sure that it gets asked anyway. The second part of that question is, how do you ensure the quality and realism of these synthetic data sets?
The quality, we make sure that we have a pre-cleanup process, which means any data that's coming in, either it's from the survey side as well as the drill and blast or the loading and timing or any additional parameters, including the rock mass. We evaluate essentially with the QA/QC approach. And then the new data that we are creating, the synthetic data. Suppose for an example, just looking at the rock movement, the XYZ vectors, right? So those also gets validated by our scripting technology that we have developed. Essentially, the QA/QC of the data, so it's not like totally garbage there. So we have built a kind of a QA/QC process there.
All right, our next question is, which AI are you using? Is it off-the-shelf solution or a RAG system based on open source model?
Yeah, no, so this is trained kind of in-house. We don't use RAG because it's a combination of physics model as well as the convolution neural network. So you can search. There is a framework there. There is no kind of fully developed model we can utilize off the shelf, but there is a framework called physics informed neural network, and that there's a lot of papers has been written, and that's kind of the framework we are using. But we still our architecture kind of we have developed by taking the convolution neural network, we trained it, and then we incorporated the physics. We don't use RAG for this because it is essentially kind of our own in-house system that we have developed.
Perfect. Well, that is all the current questions that we have at this point. So thank you very much, Ravi, for taking the time to present to everybody. Thank you, everyone, for attending our webinar. As always, if you have any questions, please feel free to reach out to us at Strayos, and we are happy to go through or walk through the different platform for you or answer any questions that you might have. But thank you very much for your time today, and we appreciate it.
Thank you all.
Take care.
Bye.